Nice to meet you. Let's see. All right, can you see my slides?
Yeah, perfect. Can you move your pointer if you need it, just to see if it works? Okay, fantastic. Yeah, fantastic. Okay, so for the second talk of this afternoon, Tel Aviv afternoon, we are very happy to have Chiara Salemi from MIT. She's a graduate student there, and she's a leading of one of the leading people in Abracadabra actually. And today she's going to talk about lumped element detection for low mass axions. So please, Chiara, take the stage.
All right, thank you. Yeah, so as you said, I'll be talking about lumped element detection for low mass axion dark matter. And I'll be focusing on the two experiments that I work on, which is Abracadabra 10 centimeter, which is this small prototype experiment that we built at MIT, and DMRadio, which is a program of larger experiments that is following up on this technique. So let's go ahead and start. So this lumped element detection is looking for the axion photon coupling, like we've been hearing about. So this is the normal plot that we see. We have GA gamma gamma, the axion photon coupling versus the axion mass. And we would really like to look in this entire parameter space, but of course the most motivated area is in the yellow band, which is the axions that solve the strong CP problem. So in this talk, I'll be talking about low mass axions. And what I mean by low mass is lower than about a micro EV. And the reason I picked a micro EV is that a micro EV axion has a Compton wavelength that's about a meter in size. And the reason we care about a meter is that that's about the size of a human, which means that a detector of about a meter is something we can build. So this is the picture in our head then. So we have a general detector, and at the higher masses, we have short wavelengths that can fit inside your detector. And so you can see, basically, you can exploit boundary conditions. So this is what ADMX does. The axion resonantly rings up a cavity. At lower masses, you can see this is the picture we have. We have a much longer wavelength, which doesn't fit inside our detector, unless you want to build a detector that's maybe a kilometer or hundreds of kilometers in size. And this is where the lumped element detection technique comes in. So I'll tell you about what this lumped element thing means. But first, I do want to point out that gut scale axions have masses of around a nanoelectron volt. So depending on who you're talking to, maybe this is a particularly preferred mass to look for, and we can cover this mass range. Okay, so what do I mean by lumped elements? A lumped element model is just a description of a spatially distributed system that simplifies it to discrete entities. So the way that most of us have encountered lumped element models is in circuits, right? So you have some distributed circuit, but we make the approximation that all of the inductance is located in one place, and we call that an inductor. And all the capacitance is located somewhere else, and we call that the capacitor. So these inductors, capacitors, resistors, these are our lumped elements. So the reason we can actually make this simplification is that we're assuming that the wavelength is much larger than our circuit. So as the wavelength approaches the size of the circuit, you start having to worry about things being out of phase. You get into RF engineering. So this is waveguides and transmission lines, not a normal lumped element circuit. And this is exactly the regime that we're in for low mass axion detection. We have an axion wave that's much bigger than our detector. And so what we can do is we can actually just treat the detector as a circuit. So I will tell you about the circuit that we use for Abracadabra. But first, I want to tell you about a little bit of axion ENM, which we've heard about in the last talk. But I want to talk about how we actually use this in a circuit model, because we're looking for a current that is our signal. So this is Ampere's law. In white, we just have the normal Ampere's law with no sources and no axions. We have the curl of B is the displacement current, ddt. And then everything in orange is what happens if axions and photons interact. So of course, we have this coefficient G gamma gamma, and then we have these two terms. So I'm just gonna go ahead and ignore this first term because we expect the gradient of the axion field to be small. And we're left with this, which looks a lot like the displacement current term. And so what we can do is we can actually just write this as an effective current. We can plug in the form for the axion fields and get this out. So we have the effective current is G gamma gamma times the square root of 2 rho dm. So we're looking for dark matter axions. So if there's more energy in axions around us, there'll be a larger current. The current oscillates with a frequency that is the axion mass. And then there's this magnetic field here, which as the experimenter, I supply this magnetic field and the axions will come interact with it and make a parallel oscillating effective current. Okay, so this is the signal current in our circuit. All right, so the experiment I work on is Abracadabra 10 centimeter. Abracadabra is an acronym. It stands for a broadband/resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. And I always have to put it on the slide so that I don't forget what all the letters stand for. But it's very descriptive. We've already heard a lot about cosmic axions, and I'm going to tell you about this amplifying B-field ring apparatus. This is our detector right here. This is a superconducting shield that actually holds the magnet inside it. And then almost everything above it is just the cryogenics. This is the dilution fridge that cools it down to millikelvin temperatures. Okay, so let's talk about how lumped element detection works in Abracadabra. So on the right side right here, I have a diagram of the Abracadabra detector. And then on the left side, I have an equivalent circuit. So we're going to step through this circuit and see how it actually translates into a real detector. The first ingredient I need is a magnetic field to source our axion interactions. So in Abracadabra, we have a toroid. It's this blue thing right here. And it's very small. It's about the size of a grapefruit, but it has a 1 Tesla field, so it's decently strong. If axions exist, they'll come and interact, and they'll set up an oscillating current parallel to those B field lines. And so you can see in our circuit diagram, we just have a current source. It's that simple. We want to take the effective current from the axions now and translate it into a real current in our circuit. And so we can do that with just an inductive coupling. So in our circuit diagram, we have a transformer. In the Abra detector picture now, we go from an effective current sourcing a real oscillating magnetic field around it. And then if we put a pickup structure in the central bore right here, we can basically just collect those flex lines and we have a real current that's sourced going around like this. Okay, so now we have current, real current circulating in our pickup circuit, but it's very small because it's suppressed by Ga gamma gamma. We don't want to just leave it circulating in our pickup though, we want to actually read it out. And so what we do is we put a slice in this pickup and we redirect the current to go out through some wiring and amplifying it using a SWID. It doesn't look like this, it looks more like this. Okay, so we went from an effective current to a real small current in our pickup to a larger real current on the output of our SWID amplifier. And now we can use that to look for axions. So we take our data coming out and we Fourier transform it to look in frequency space. And if there's an axion there, what we'll see is a very sharp peak right at the axion mass at that frequency that that effective current was oscillating. And of course, there's some width that's determined by the velocity dispersion of the dark matter. And so this is the signal that we're going to be looking for. So this is the Abracadabra detector. And here's some data from our most recent run. So on the y-axis, we have the magnetic flux in our pickup. And then on the x-axis, we have the frequency of our signals. And just to orient you, a nano EV axion sits right in the middle of our frequency range. So in blue is the actual physics data. This is data taken with the magnet on. All right, so what we want to do is we want to take this and we want to translate it into either limits on Ga gamma gamma or a discovery of an axion at a certain coupling strength. So there are a few things we need to do first. You've probably noticed that there are a lot of spikes on this blue spectrum. Unfortunately, they're not all axions. So we have to go through and remove all these backgrounds. The orange curve right here is data that we took with the magnet off. So we know that J effective is proportional to the magnetic field. So if B goes to 0, the current goes to 0. So if we have a spike that's in both spectra, that means it's not an axion. So we can get rid of all of these. And there are a lot of other cuts that we can do. You can see there's a lot of peaks down here at low frequencies. These are vibrations. Actually, if we demodulate our data, we can listen to local radio stations. Those are all at known frequencies, so we can get rid of those as well. And we have lots of other things we do to reject backgrounds. So the other thing we need to do is we need to figure out how to translate this pickup flux into units of Ga gamma gamma. And so to do that, we do a full end-to-end calibration. We actually have a wire running through our magnet. And so we can inject just oscillating currents onto that mimic an axion signal. And we can get the full detector response by seeing how that responds on our digitizer. And then finally, once we have it in J gamma gamma, we can fit an axion signal. So we can look for this signal shape. We can scan it over our entire spectrum and do a full log likelihood analysis to see if any of the remaining peaks are actually axions. So that's what we did. In blue are the limits from the first run, and in black are the limits from our most recent run in 2020. And this is actually very downsampled. We have millions of mass points. So a third of our limits lie at the bottom of this green band. To give you a little more context, I can zoom out. So there we have it in pink now, the first and most recent runs of Abra 10 centimeter. And you'll notice that we're actually just barely starting to stick out beyond the cast exclusion, the cast experiment, which looks for solar axions that we heard about this morning. So we're very excited about this. This is a baby prototype detector that's a quarter for scale. And even with that, we have world-leading limits. So since the first results were released from Abra, a couple of other experiments have come online using the same lumped element detection technique. The Shaft experiment and SLIC both released results. And so you can see that there's a lot of excitement brewing in the experimental community about actually being able to build experiments looking for axions in this mass range. You might have noticed, however, that there's a lot of white space here. We have to get some 7 or 8 orders of magnitude before we can reach down into the QCD band. And unfortunately, these prototype detectors are not going to be able to do that. So the next step is scaling up. And so that's the plan for the DMRadio experiments. So how is DMRadio actually going to achieve several orders of magnitude improvement in sensitivity? There are a few different ways. And the sort of low-hanging fruit to improve the experiment is just to build a bigger magnet with a stronger magnetic field. Unfortunately, this is also the most expensive thing you can do to improve your experiment. And so we're really going to bring out the whole arsenal of ideas to improve this. So there's lots of things we're doing. I've just put a few on this slide. We can improve the coupling from the axion current into the pickup. It's just improving that transformer. We're going to go from a broadband readout where we look at all frequencies at once to a resonant readout similar to ADMX, where we have a very high sensitivity and narrow range, and then scan. We have some ideas for how to optimize both the scan strategy as well as the impedance of our circuit, as well as ways of reducing noise. So at low frequencies, Abracadabra was limited by vibrations. And so we have some systems in place to reduce vibrations, electromagnetic interference, and other noise sources. And then finally, at the lowest frequencies, where G gamma gamma is very small in the QCD band, we're going to use some quantum acceleration techniques to eke out that last bit of sensitivity. So this is similar to what Haystack was doing at high frequencies, but adapted for a low frequency experiment. Okay, so here are the different generations planned for DMRadio. The first one, DMRadio 50 liter, is actually about to start construction. And you can see it looks very similar to the Abracadabra 10 centimeter experiment, except that it's bigger. So Abra was about a liter in volume, a little less, and DMRadio will have a 50 liter volume magnet. It has this same toroid shape. The pickup structure is a slightly different geometry, and it will have a resonant readout. But otherwise, it's pretty similar. The following generation will be DMRadio meter cubed. Meter cubed is currently funded for a design study through the DOE Dark Matter New Initiatives program. And so we've been hard at work getting this design working. And you'll notice that this is actually very different looking from both Abra and the 50 liter experiment. The red right here is actually the magnet. So it's a solenoid design instead of a toroid. And the reason we're doing this is because meter cubed will be looking at higher frequencies, butting up against the micro-EV line where I said there was a transition between the low and high mass regimes. So basically, as you go up there and the wavelength shrinks, you start running into some parasitic resonances. And it turns out that this solenoid design avoids some of those resonances that the toroid runs into. And then finally, we have DMRadio gut, which I don't have a picture for yet because it's still just an idea. But this is basically the ultimate experiment for this lumped element detection technique. With DMRadio gut, we plan to get DFSC sensitivity to nano-EV axions. It will require some technological advances, but there are multiple different paths to get there. And so we really do think that this is achievable. And I'll put a little advertisement out. We're hoping to release some papers on the archive this week for the meter cube design and for the R&D paths for DMRadio GUT. So be on the lookout for that. So this is the reach that we expect from the DMRadio program. DMRadio 50 liter will not be able to reach into the QCD band, but it will be able to probe axion-like particles over a very wide range of masses. As I said, oops, there you go. Meter cubed will be at higher masses, and it will be able to go all the way down through the QCD band. And then DMRadio GUT will be in the QCD band all the way to these low masses. Okay, so to summarize, lumped element detection is a powerful technique for probing low mass axion dark matter. And the Abracadabra 10 centimeter prototype showed that this technique works, and in the process at world leading limits. And so now it's time to scale up with the DMRadio experiments. Okay, and so I just want to thank you all for listening, as well as my collaborators on Abracadabra and DMRadio.
Fantastic. Thanks a lot, Chiara, for the very nice talk. So now, as usual, it's time for questions. Let's see. Eduardo has a question, so if there are no other...
there are questions from you.
You were the first anyway, so let's be meritocratic. Whatever. You can go ahead, and then we can go back.
I was wondering, like, you use a magnetic field as a veto, and do you have all the data stored? Because for example, you might have discovered dark photon, for example, and you don't know about it, right? Perhaps you already discovered it and you just throw it away.
So we do have old data stored, but we actually can't look for the dark photon with Abra 10 centimeter. The geometry doesn't work. But for the meter cubed experiment that has the solenoid geometry, you can, if you swap out to a different pickup structure, you can look for the dark photon with that, and we plan to.
So what kind of alternatives are you planning to use as a veto in general, as a check on your data?
It's hard. I mean, being able to shut the magnetic field off is a very powerful veto, as you saw in our data. So the biggest thing is just reducing noise more. So we had a lot of background peaks in the Abra data that we are confident we can get rid of. So the vibrations at low frequencies, the only vibration isolation system we had was the magnet was hanging on a Kevlar string in a spring. You can get a lot more sophisticated than that. And the shielding was just one layer of superconducting shielding. We have plans for multiple layers of superconducting and normally conductive shielding. So it's harder to say confidently that you definitely have a dark photon, because you can't do that turning off the magnet process, but you can at least get rid of a lot of the backgrounds.
I see. Thanks.
Okay, thanks. Any further question for Chiara? I have actually a short one before anyone show up. Like in terms of time, it's always difficult to say so, but given it's so exciting in terms of time scales for the future, so for 50 liters and meter cube, which are the time scale that you have in mind, like the funding that you already have, this kind of stuff, just to have an idea of the landscape?
Yeah. So like I said, 50 liter is starting construction. We are hoping to have first results within the next couple years. Meter cubed would be starting construction while 50 liter is taking data. And so that's like 5 to 10 years. We don't have funding yet, so we don't know. That would definitely be more long-term, especially because we do have this R&D that needs to happen in the meantime.
Okay, thanks. Any other question? Let's see. Okay, I don't see any other questions, so I think that we can thanks Chiara again and stop the recording of this talk. Thanks, Chiara. And we can stop the recording. Mine's